Hi, welcome to Number Systems tutorial video. In this video, we are going to look into how the binary number system works. Okay, so first of all, why we need binary systems? Um, so basically, in computers are nothing but complex circuits. So circuits it's a device where we manipulate electrical signal. So in computers, we'll have a wires, many wires, and then we'll measure the voltage of that wire. If that wire, if there is a voltage, say for example 5 volt, there is a voltage, then we consider that as high, right? If there is no voltage, zero voltage, then we consider that as low. So logically, we have two states to represent the values, right? One is there is voltage here and there is no voltage here. So since we have only two states, that's why we have a binary system here. That's what we are explaining here. Like basically, it is just having two states here. And another interesting thing we need to note is we can't exactly get, like, say, for example, if this is the 5 volt, this is just for your knowledge. If there is a 5 volt here, we cannot exactly in the middle we say this portion is um, low and this is high. The reason is it can be the electrical signals can flip based on some outside circumstances, right? So that will lead to a lot of inconsistent state. So that's why we have um, a huge gap, right? So this is an illegal area, like this is an illegal place. This area is illegal, and anything in this range, it's called 0 volt or low, right? And anything in this range, we call it high. So logically, how we represent these states are something like 0 or false, right? Or low. They all represents the same value or same state, okay? In the case of high, we say it may be logically 1, or we can say it is true, or we can say this is high, okay? So that is the reason, since we have only two states, that's why we have a binary system, binary number system in computers. Okay, so let's go deeper about how the circuits and binary number systems are connected. Okay, so in this case, let me explain this picture in a more detailed way. Suppose I have a circuit here, okay, and I have one wire here, for example. Assume that the circuit is a black box and I have one wire here. And when I try to measure the voltage in this wire, the possible values will be either 5 volt or 0 volt. Okay, I have one wire, right? one wire, possible values are two values. Okay, you can see the correlation here. Basically, it is 2 power the number of wires. Okay, let's see. Say for example, the next example, we'll build this idea. Okay, suppose I have um, two wires here. Okay, same circuit. So if I have two wires, say in this case A and B, so how many possible values I can represent using these two wires? Say again, let's draw the table here. So it's not simple 0 or 1, right? A, B. So something, these are all the combination, right? So this is the maximum combination I can get, right? So the values will be either 0 or 1 or 2 or 3. So the range is, I can represent four values, the range from 0 to 3. Again, the correlation here, the relationship here with the wire number of wires is like, it's again 2 power the number of wires. The red one represents number of wires, right? So that represents 4. I can represent 4 values. In this case, I can represent 2 values. These 2 values are 0 and 1. In this case, 0 and 3. Suppose we expand this to, I'm not going to expand further and further. This is just to want to basically, I want to give the foundation, like how these things are coming, like how we got this, right? Suppose we have 3 wires here, right? So in this case, we will have A, we will have B, and then we have C, okay? And then the output value. So in this case, we'll have 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, right? So the value here, this is 0, this is 1, this is 2, this is 3, this is 4, and this one is 5, 6, and 7. So with 3 wires, we are able to represent like 8 values, right? 8 values. So the range is somewhere from, the range is 0 to 7, right? So again, the relationship maintains here, right? It's 2 power the number of wires, right? Number of wires it is. So again, 8 values. So if we have something like, so we can generalize this, right? Suppose I have a circuit, right? And I have like, say for examples, I have n wires. So how many values I can represent? It's pretty known from our relationship. So it'll be, again, 2 power the number of wires. In this case, we have n wires, right? That's the number of wires. So we have 2 power n values we can represent. And the range will be 0 to 2 power n minus 1. So why it is 2 power n minus 1? Since we have a number system, right? Decimal number. What do I mean by decimal number? It is base 10. So there is a history why we are using base 10 numbers. So the reason is in the olden days, I don't know the history, but somewhere in Middle East and as well as in India and other places, the traders used to count their prices or compute their prices using their fingers, right? So since we have 10 digits, 10 fingers, so we started using the decimal number 10, right? Based on this, we have oldest computer some people call abacus. Please go and search in the Google, right? I'm not going to, this is not an history lesson, but this is how we get the um, decimal number system. That's what we use in our regular day-to-day life for anything, right? So suppose this system, again, it's based on weighted positional number system. Okay, what do I mean by that? So let me explain this. It's an example. Okay, suppose I have a number like 163, which is a decimal number, right? How this is the value is actually computed is, so we have 1, 6, 3. The first position is zeroth position. That's 10 power 0. And then the second one, we have 10 power 1. And then the third is 10 power 2, right? So that means I have 1 10 power 2 number is here, plus I have 6 10 power 1 number is here, and then I have 3 10 power 0 number is here, right? So what is 10 power 2? It's 100. So 100 is here, and then I have 6 tens are here, and then 3 ones are there. So that's why it's 163, right? I think we all know that, right? This is how the decimal number system works. Say, for example, in this case, right? So that's what I explained here. So we have 329. So the red one clearly explains 10 power 0, which is the ones position, and 2 is 10 power 1, and 3 is 10 square, that's the 100 position. So I have 3 hundreds here, and then I have 2 tens here, and then I have 9 ones here. The decimal number is 329. Okay, so something like that. So in binary number system, we have the same idea, but in this case, we have base 2. Okay, so suppose this 101 is our binary number. The rightmost number, we call it as least significant bit. Since every binary digit, it's called a bit. I'll go through some other terms in the later stages, okay? So here we have the least significant bit, and here we have the most significant bit. Like 10 power zeros, in our case, we have everything in binary. So the first digit, least significant bit, is 2 power 0, and this is 2 power 1, and then this is 2 power 2. So I have 1 2 power 2, but I have 0 2 power 1 representation, and I have 1 power, that is 2 power 0, which is 1's representation. So I have 4 plus 0 plus 1, this number is 5. Okay, similar like that, we have few more examples here. So here I have something like the least significant bit like 2 power 0, and then I have 0 2 power 1, and then I have 1 2 power 2, and then I have 1 2 power 3, right? So in this case, I have 1 8 and then another 4 representation, but there is no 2's representation here, but I have 1 1 representation. The addition of that is value 13. Okay. So let's do this simple calculation. So this is our first um, conversion, right? This is the key. So suppose I have a 8-bit binary number. Okay, so this is converting binary to decimal. We just saw that in an easy example. So this is, I'm again representing using a number system. So this is an 8-bit numbers. Okay, so 8-bit means I have 8, right? It's equivalent to 8 wires in our previous example. Okay, so in this case, this is what we call it LSB. Each one is bit, right? This location is a bit, right? Okay, so 0, 1, 1, 0, 1, 1, and then 0. Okay, so this bit we call it most significant bit, right? So like weighted positions, we are going to name this. So this is 2 power 0, this is 2 power 1, this is 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, and then 2 power 7. So in this case, I care about the numbers where the actual, like it added the value, right? Wherever 0, it's not representing inside, like it's not adding any value, right? It's 0. So I'm going to consider only the numbers which are weighted, like which are actually representing in my value. So in this case, I have 1 2 power 6, right? And then I have 1 2 power 5, and then again 1 2 power 3, and then 1 2 power 2, and then 1 2 power 0. Okay, so that means 2 power 6 is 64, this is 32, we have 8 4 plus 1, right? So this is all right. So the value here is 101 is the decimal number. All right. So no, it's actually 109, right? So yeah, I'm sorry about the computation. It's 109. So that's the value for this number. So 32 plus 8 is 40, so 104, 108, 109. So the value is 110. That's the decimal conversion of that. Okay. So likewise, so basically here we are trying to do some simple operations. Okay, I'm not going to go too much about subtraction. Okay, that's out of the scope here. Suppose I'm adding two binary numbers. How will I add two binary numbers? Okay, so let's start with the decimal number. Here I have 9 and then 5. So 9 plus 5 is actually 14. So 14 means I have 110 and then there are 4 ones, right? That's why that 110 comes here, right? It carry over that. So that 110, so I add that 1 plus 2 plus 4, now I have 7 tens, okay? Is that clear? Now let's see, let's look at here. I have 300s here and then I have 800s here. 3 plus 8 is 11, right? So that's why we get 11. That means I have 100 and 1000 is represented here. That's how our decimal system computation works. So let's look at this similar kind of carry. Okay, so now let's consider the binary calculations. So 1 plus 0 is 1, 0 plus 1 again is 1, 1 plus 1 is 0. How 1 plus 1 is 0? Since we have a binary number here, 1 plus 1 it's 2. So we cannot represent 2. 2 becomes 1, there is 1, 2 here, right? And then 0 ones are there. That's how, like 9 plus 1 is 10, like 1 0. Here 1 plus 1 is 2, which is nothing but 1 and 0. So that's why 1 plus 1, in this case 1 plus 1 is 0. And then we carry over that 1 here, right? This 1 is carry over here. So again 1 plus 1, it is 0 here, and again we carry over that 1 here. That's why we have that 1, final 1. Okay, so this is the binary addition. Okay, all right, so let's see another interesting important concept. Okay, so we saw how to convert binary number into decimal number, right? Now we need to do the same. Again, no one, like in computer systems, they don't care about decimal or binary and all those things. So the basic idea here is we have voltage and then there is no voltage. So all we are trying to do is we are trying to encode some kind of scheme in a bunch of bits to represent numbers. It's not only numbers, the bits can be represented as text, colors, sound, and so many ways. What are all these things? They are nothing but datas, okay? We'll go through that in a very last portion of that, like the application of that, okay? So we want to see binary to decimal to binary. Suppose I have a number like 163 base 10. How do I convert this into a binary number? Okay, there are two ways you can do this. I'm going to teach both ways here. You adapt, I mean, you follow whichever is comfortable for you. Okay, so first way, right? Number one option. So in this case, we'll just have some side calculations. We need some 2 power values, okay? 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 is 16, 2 power 5 is 32, right? 2 power 6 is 64, 2 power 7 is 128, and then 2 power 8 is 256. Okay, so let's have this for our calculations. Okay, so now what we need to do here is say for example 163 is here. So where is the 163 falls, in which range? Okay, it is false between 2 power 7 and 2 power 8. So that means I have a representation for 2 power 7 because which is smaller than 128 is smaller than 163, but it is 256 is much bigger than 163. So that means I don't have any representation for my like 2 power 8 bit. Okay, so what I'm going to do is I'm going to say 128 here. Okay, and then I'm going to say I have a 2 power 7 representation here. Let's do the subtraction. So 13 minus 8 is 5. This becomes 5, right? So 5 minus 2 is 35. All right. All right. So now 35, we do the same kind of. Is 35 bigger than 64? No. But 32 is smaller than 35. So definitely I have 2 power 5 bit position is present in this number. Do you see that, how this whole thing works? I think you get the pattern here. So 32, right? 2 power 5. So in this case, 35, so it is like I have 3, right? So if it is 3, then 2 power 2 is bigger than 3, right? It's a larger number. 4 is larger number. But definitely I have 1, 2 is there, right? So I have 2 power 1 is here. That is 2, right? That is 2 power 2. So that is 1. So then I have 2 power 0 representation is also is here. Is that clear? To anything power 0 is 1. So let's draw this. Let's place this value. Okay. So this is an 8-bit system. Okay. It starts from 2 power 0, right? 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, and then 2 power 7. Okay. I have 1 2 power 0 bit is here. So that is, I have the representation, but there is no 2 power 6, but there is 1 2 power 5. Okay. And then there is no 2 power 4, no 2 power 3, no 2 power 2, but 1 2 power 1, and then 1 2 power 0. So this is the binary conversion of 163. Okay, this is one way to do that. The other way to do that is nothing but a long division. You might have seen that in your, you might have done that during your middle school or elementary school, I don't know. So basically here 163, right? We start dividing this by 2. So in this case, this will be 81, 0, right? And then 81 divided by 2 will be 40. Um, Actually, there is a remainder 1, right? 162, the remainder 1. 40, there is a remainder 1 here. And then 40 divided by 2 is 20, that is remainder 0. And then 2, remainder 0. And then 2, 5, remainder 0. When the 5 is divided by 2, we have 2, and there is a remainder 1. When you do 2, this is 1, and then 0. All right. So we have to place our number from this direction onwards. Okay. So first we start with 1, 0, 1. I mean, it starts from here, right? 1, 0, 1, 0, 0, 0, 1, 1. Okay. So that's how we are going to write 1, 0, 1, 0, 0, 0, 1, 1. So it's the same result, right? This is the equivalent of 163 base 10. Okay, is that clear? So this is the conversion of decimal to binary number. Okay, so here again, I just explained that in my slide, right? I just walked through with you. So in this case, it's 125 So 125 divided by 2 is 62. This is like a long division way of they are trying to do. Okay, they are divided by 2 options. You can do either way, whatever the way I said, like whichever is convenient for you. You can use this way. Some people find it easier this way, but some people find this is easier. Okay, so here I'm just representing one way. So 125, 62, and then the remainder is 1 here, right? That's the bit 0 representation, bit 0, the least significant bit. So on and so forth, you divide that, and this is the result, you're getting it. Okay? All right. So this is another way, like the second method I was talking about, that the largest power of 2. So here, like the way I worked it, so you have 0, 1, 1, 2, 2, 2 is 4, 2 power 2 is 4, 2 power 3 is 8. So we have the numbers like that. And then 112 is bigger than 128, larger than, smaller than large 128, and smaller than 64. So definitely there is a 2 power 6 64 number is present here, right? So we have a bit 6 present here. So 112 minus 64 is 48. If you consider 48, 48 is definitely larger than 32, right? So I have a 32 representation. So 48 minus 32 is 6. So I have a bit 5 position is there. Then 16, that means definitely it's just squaring up. I have 116 is there, so 0. So I have bit 4 represents here. I have a bit 4 representation, bit 5 representation, and then bit 6 representation. Apart from that, I don't have any other bits. Okay, that's the um, conversion here. Okay, so I already explained in my other example, so you should be easy to follow this. All right. Okay, let's consider this is again more for your knowledge, because this is anyone uses number system. It's not only NAS 110, any course related to computer science, this number system might be useful to you. Okay, in this case, there are three common basic logical operations we use in computing system. Okay, one is and, another one is or, and another one is not. Okay, let me explain this, and then we will go through in detail later. So what is and? So in day-to-day life, right? So we say it is like it's windy and it's raining, so I'm going to take my umbrella, right? So it's things like that, all right? So today I am going to have an Indian food or a Mediterranean food, okay? Something like that. That's how we do it. Things like in our regular day to day life, we use always be, right? So if A and B are false, the outcome will be false. On the other hand, if A is false and B is true, again the outcome will be false. Likewise, if A is true and B is false, the outcome will be false. But in the case of A and B are true, then the outcome is true. So it's true one and only the situation is if both the operands are true in the case of AND operation. That's why we always say in AND false dominates. If any one of your operand is false, it doesn't matter how many, even if you have a gazillion number of truths in your expression, the outcome will always end up false. So that's why in even computing, if I have a complex expression, if one of the operand ends in false, I don't need to calculate, evaluate the other part of the expressions. Okay? It's false and anything, it's always false. Okay? So we don't waste computing resources. We short circuit and then we simply say the outcome is false. Okay? Likewise, in the case of OR, it's diametrically opposite. So in the case of OR, true dominates. So let's look at this. If A and B are false, then it is false. But if A is false and B is true, the outcome will be true. If A is true and B is false, again the outcome will be true. Or, like, if A and B both are true, the outcome will be true. So you can clearly see that if any one of my operand is true, the outcome is always true. So in the case of OR, true dominates. So if I just evaluate a complex expression, it's an OR expression, and then basically if one of the operand evaluates to true, I don't need to evaluate the other part of the expression. True ORs with anything, always true. Okay? So in computing systems, we use some short circuits to make a program faster in our solving the problem. And also, we don't want to waste computing resources. That's a simple short circuit we used to take. Okay? In the case of NOT, which is one of the most important logical operation, it's pretty straightforward, right? If true, you not the true, it is false. You not the false, it is true. Okay? Based on this, let's see this. Okay? So in the case of AND, so here we have one operand and then we have another operand. So you can clearly see that 1 and with 1 is true. In other cases, it's always ends up with 0. So the square bracket here, like 1, that's the only situations, right? Like, so 1 and 1 is true. I mean, 1 and 1 is 1, but anything with 0, you add that, the resulting outcome is false. Likewise, in the case of OR, right? So if anywhere it is true, right? Here it is true, true. This is the only case. This is one of the case, like false and false or false, it is false. Again, false or false, it is false, right? 0 or 0, it is 0. So that's clearly explaining a little bit more, like with the more operands. In the not, if it is true, the outcome is false. If the false is your input, the outcome is true. It's exactly opposite of that. All right. All right. So let's look into the last part of our number system video. This is hexadecimal system. Okay, so why do we worry about this X digits? So here I want to give you some brief knowledge about few things. Okay, this might be very useful for you. So pay attention here. So every wire or every position, we call it bit, right? So that's called 1 bit, small bit. And then if you have 4 bits, right, that's called a nibble. Okay. And then if you have 8 bits, It's called a byte, right? Big byte. Okay. And then if you have 1,000 bytes, right? It's called 1 kilobyte. Okay. But this 1,000 is very interesting. Okay. So it's not exactly 1,000. Okay. It's actually 2 power 10. 2 power 10 is 1024. So they approximate that 1024 bytes are 1 kilobyte. Okay. So if you have 2 power 20, that is 1,000 by 1,000, which is million, which is 1 megabyte. Okay. Likewise, you have 1,000 times 1,000 times 1,000. That's 1 billion. It's 1B, right? This is 1 million. This is called 1 megabyte, right? This is called 1 gigabyte. Okay. Try to remember this basically. So this will help you in your other computations. All right. So in the case of hex, hex is not a very, there is no real encoding scheme or anything like that. So why do we worry about X? The interesting part is if we have like 1 0 0 0 0 1 0 0 0 1 0, this is very difficult for me to remember. Imagine we are nowadays dealing with 32-bit systems and also 64-bit system. Most of our computers are 64 bits now. So if you have, remember, imagine like if you have 64 ones and zeros, our head will be spinning. So there should be an easier way for us to represent this, like cumbersome number of like this is very cumbersome, like remembering this number of bits, right? So what we are doing is we group these bits into nibbles. Okay. So and then 4 bits, one nibble, it's actually one hexabit number. Okay. So in this case 1001. So it's like actually 2 power 3 and then 2 power 1. So basically we have 9. In this case this is 0. Okay. In this case we have 1, and then in this case we have 2 power 3 and then 2 power 2, which is 8. 8 plus, I mean 8, 2 power 1. 8 plus 2 is 10. In hexadecimal we call it A. So this number, so I'm going to go in deeper, but I'm going to explain in a bit slow, but what I'm trying to say is we group 4 bits and then each 4 bit represents one X digit. So, 4 bits, 2 power 4, 16. That's why we are using hexadecimal number. Okay. So in this case, we have a table here, right? So if all my bits are 0, then my hex is 0 and decimal is value is also 0. Likewise, this is 1, 2, all the way. 1001 is 9. Why? This is 2 power 3, 8. 8 plus 1 is 9. So I have a x9. But in the case of 10, enough digits, right? I cannot say 1 0, right? 1 0 is a decimal. But in the case of x, I represent 10 as A, 11 as B, 12 as C, 13 as D, 14 as E, 15 as F. In 15, all the bits are set. We call it, when there is a 1, we call the bit is set. Okay? So let's dissect into this E, right? Let's see E. So how this is 14? So 1, 1, 1, 0. We call this is 14. Okay. So y? 2 power 3, 2 power 2, and then 2 power 1, and then 2 power 0. So I have 1, 2 power 3 is there, right? So 8, this is 4, this is 2, so I have 14. All right, and 14 in x is e. All right, so you need to remember this convention. It's pretty easy. 0 to 9 we just represent same, but 10 to 15 we don't have enough digits, right? So we say A to F, right? That's all it is. So just remember that 10 is A, and then 11 is B, so on and so forth. All right. So based on the weighted positions, right? It's the same weighted position rule. So in this case, I have an X number, right? A to B. So this is a hex number, A to B, right? So I can represent this number like A to B, right, base 16. Okay. What that means is I have 16, like 16 power 0, 16 power 1, 16 power 2, right? This is 16 0 position. There is 116 here. There is 16 square, like that many number of like 16s are there, right? 256. Like 10 square, we have 16 square here. All right. So B means it's 11. There are 11 ones are here. Okay. Two 16s are here, right? This is two 16s are there. And then there is 10 256 positions, like representation is here. Okay, that's the representation. Let's it's becoming more hairy, like if you go bigger number. Okay, but let me convert this. Okay, let's convert hex to decimal. All right, so this is the number. We always represent hexadecimal using hex B24, right? So this is how, so the decimals in computing system, we say 2. That means it's a decimal number 2, our regular number 2. If it is x, we say x a b 2, right? That's a hexadecimal representation. Okay. All right. So in this case, let's look into this. I'm going to convert x into decimal, right? So in ones position, I have 4 ones are here, and I have 2 16s are there, and then there is 11, B is 11, right? 256 are there. So that's what we represent here. But when you calculate all those things, the resulting number is 2,842. That's the hex conversion for that. Okay, 242 is that base 10. So you convert the hex to decimal. Mostly, you you don't need to really worry about you like, oh, 16, it's really a big power. You will deal, this is more for your knowledge. Try to know like what's the concept behind that. You may not be tested in your exams like making a huge calculation in your head. Okay, this is, you need to know the fundamentals, like why are we dealing with hex number, which is so weird, right? The interesting idea is we group a big chunk of bits into 4 bits, and each 4 bits represents an X number. So in that way, 32-bit can be represented using 8 X bits, which can be easily, we can at least have an idea like what's happening. Okay, I'll give you some examples of the application where you'll appreciate that. All right, so in the case of decimal, right? How to convert a decimal into X. So it's a similar idea, right? In the case of binary, we divided everything by 2. In this case, we need to divide everything by 16. So we have a 386 number, it is base 10. So you divide 386 for 16, then you got the remainder like 24 and then 2, right? So the 24 you divide again by 16, it's 1 remainder by 8. So the idea here is the answer is 182 is the hex digits. Okay, so let me explain how you are getting this number, right? It's the same thing. You have one um, 16 power 0, right? That's the remainder 2 here. And then basically you have one, I mean, 8 16s are there, right? In this case, 8 16s are there, right? And then you have one representation of one 256 is there, right? This is the number we are talking about. So that's the hex conversion. So generally, again, you will not be asked to divide a huge number here. The basic concept is you divide the number, right? 386, you divide that by 16, you'll get 24, and then the remainder is 2, right? And then again you divide the 16, 116 is there, and then the remainder is 8. So again, we need to look into this way. So 182 is the hex representation. Okay, so that's it for most of the things. Let me explain. So again, so the reason we are looking into hex is again we want to we don't want to deal with huge, like, see, remembering this many number of binary digits is very difficult for me. This is a 16-bit binary system, right? Sometimes we, in the olden days, we have a 16-bit computers. So this representation is too difficult. That's why we group 4 bits and then we convert that into hex. This is more manageable for me to at least remember this or handle that, okay, compared to the 0001. So in this case, the blue one is 5, right? In this case, the 4 digits of the binary, again, it is 3, right? And then 1011. So there is 8 is here, 2 is here, 1. So this is 11. That's why it's B. And then this is 4 plus 2 plus 1, that is 7. Okay, that's how we convert into hex. This is a quick way of converting binary to hexadecimal. This is very key. So you definitely need to remember this table for if you really wants to go in um, higher computing science, right? You need to have this. You need to remember this like your back of your palm, right? Like it should be really really key that you know this by heart. All right. So that's how the binary to hex is easy. So 4 bits is one hex representation, right? So you do this like again, 4 plus 2 is 6, 1 is 8, 8 plus 2 is 10, 10 plus 1 is 11. That's why it's B. Same like 7 and then 9, right? That's how we are representing it. So we already see hex to decimal, so I'm not going to repeat that. Now we comes to the last part of our discussion, which is where exactly this kind of binary system, why do I really need to learn this? So First of all, when you're trying to use certain things, like if you're trying to be a computer science engineer or network engineer or anything, you deal with the data is represented by bits. So you need to know how your data is represented, in what kind of encoding scheme is applied, and also when you're manipulating that data, for example, like you're noting, you're adding, or you're adding, and all those things, you need to know whether your system is really working in correctly the way expected way it is working. If there is any issue, you should be able to troubleshoot. That's why we are learning this number system. Okay, it's not that they are trying to torture you or something. So one classic example is when you are dealing with building a complex software system like operating system or like a network server or something like that, most of the time you might need to your memory address, right? The address of your memory is also a data. Okay, if you have a 32-bit systems, then we have 32 bits. Every address, every location is represented as 32 bits. So we need to know how to represent our memory address in X or binary. See, again, 32 bits is really huge. If I have 8 digits, like hex digits, it's easy. It's difficult again, but it's better than 32 bits, right? Likewise, the IP address, we deal with 32 bits, right? So it is like, suppose you are this 8 bits, for example, we have IP address something like 192.168.1.20 or something like that. So all these things are 8 bits. Okay, you might have think like, why my IP address, my it never gone beyond 255, because the maximum range in 8 bits you can represent from 0 to 255. That's the value you can represent. So there is no IP address starts at 256. You should know that. Okay. Likewise, the Unix file system, right? So I will go through Linux workshop again, Linux tutorial video. There I'll explain more. Each file bits, I mean the security